In this last problem, we're going to see that there are different types of potential energy. So we're placing a rocket on a spring to launch it in the air, and we want to know how high it goes. So we have to do our before and our after picture and look at all of the energies. So before, we have a box, and it's on a spring. And then after, our spring is fully uncompressed, and our box is somewhere in the air. We're told that the mass of the box is 2 kilograms. We're told that the spring constant, K, is very high at 50,000 newtons per meter. Its initial length, L0, is 2 meters, and it's compressed down to a length of 80 centimeters. So we're going to call that Y initial, 80 centimeters. That's 0.8 meters, so let's just convert that right off the bat. And we want to find, when it's released, the spring is shot straight up, how high did it go? So we want to find H. So this problem has 3 types of energies: kinetic energy, U from gravity, and U from the spring. Remember, kinetic energy is 1/2 mv squared, gravitational potential energy is mgh, and spring energy is 1/2 k delta s squared. So here, this is 0.8 meters. So before, total energy is equal to the kinetic energy initial plus the gravitational potential energy initial plus the spring energy initial. It's not moving, so this is 0. But it's also not on the ground. So this, the gravitational potential energy, is not 0. So we have m g h plus 1/2 k delta s squared. So our mass is 2, our g is 9.8, our h is 0.8 because it's not on the ground. This is plus 1/2 k, 50,000 times delta s squared. So it started at 2 meters and went down to 0.8. So delta S is 2 minus 0.8, which is 1.2 meters. 0.2 meters squared. So it's very important to keep your variables in check because our height is not the same as our delta S. They are different, and it's important to keep them in track. So our total energy is, if we grab a calculator, 2 times 9.8 times 0.8. This is 15.68 plus a very, very large number, 50,000 times 0.5 times 1.2 times 1.2. 36,000. 68 joules. So our energy is very high, and it's almost all in the spring, which makes sense because our spring has a very high spring constant. So if we go over here, E final is equal to the kinetic energy final plus the gravitational potential energy final plus our spring final. This one's a lot easier. If we're at our maximum height, our velocity is 0 because we're turning around. Also, we're no longer compressing the spring, so the spring potential energy is also 0. So that's just mgh. M is 2, g is 9.8, h is our unknown. So 2 times 9.8, 19.6 h, that is our final energy. And then all we do is zoom out a little bit. 360,115.68 E initial equals E final. It's equal to 19.6 H. So if we divide both sides by 19.6, we get that H is equal to 36015.698 divided by 19.6, which is 1,837.5 meters.